they're gigantic bag of custom kernels, well, generally they get built for the industry-leading hardware. And then if you try to bring up a new chip, you try to integrate with anything else, suddenly you run into this challenge of, well, okay, I can implement VLLM, but step one, rewrite all of the kernels for all of the models, and wait a second, this is not a reusable framework. This is a very useful tool, of course, but it wasn't really designed for this modern era. So, we've been working on this for quite some time, and we've been working on the different bits and pieces, and like innovating in the space is very complicated. And so today we're excited to introduce and reintroduce the Max framework. So this is a fully new Gen AI native AI modeling and serving framework, and it's built from first principles for the modern world. Now, Max framework being built from the ground up, a lot of us have worked on a lot of these different systems. We're paying attention to all the cool research papers. We're seeing all the innovation that's happening. And we have the opportunity to build a next generation system. And so when you have the opportunity to build a next generation system, well, first of all, you can bring the best ideas from everywhere. We're shameless. We'll take good ideas wherever they come. Right? But I also feel a burden of responsibility. Because if you're going to do this, you should do it well. You should think about the implications. You should try things. And when you make a mistake, and we have, you should take a step back and fix it. Right? You should be really deliberate about building a large-scale system. And so at Max, you've got all the performance of graphs. Because graphs are a great way to get high-performance systems going, and it's really important for particularly modern workloads. We want it to be easy to use. We want to provide lots of models. We want to have an amazing graph compiler. We want to make it easy to learn and for people to build into this ecosystem. Turns out one of the best things about PyTorch is eager mode. That's amazing for exploration and discovery, and so you need a world-class eager mode. Also, the performance of graphs. Right? We want it to be portable, of course. We want to take advantage of Mojo because I think the Mojo is pretty cool. And what we won't talk about today is that none of this technology is actually specific to Gen AI. This is where a lot of the pain is, and this is what we can use to justify building these tools. But if you want to do quantum computing or biochemistry or digital signal processing or anything else totally wacky and crazy, it's all about pushing around a huge amount of data and building and orchestrating a computer. And these tools and these techniques should be native and should be able to work for that, even though it's not modular structures. So today, as Mike introduced, we're going to be talking and pulling back the covers on, say, their graph compiler. And Ferris will nerd out about MLIR internals and other cool stuff like this. And we'll learn how easy it is to program LLMs. And we'll talk about eager mode and how we're going to push the state of the art the world forward with. I'm really excited about the deep dive talks that we're doing today. And so if you look, so today, Max covers this full spectrum. You can design and build models, which we'll talk about. You can get good performance, talk about. One thing we're not going to talk about today is serving, because we didn't have time. But we'll focus on the first two, and we can talk about the third one and everything. So one of the other cool things about Max is it's pervasively open source. So if you go dive into our repository, you can see lots of different models, and there's more all the time. This is something we're continuing to invest in. We're making it out. We'll work with a lot of design partners and customers on this, which is cool. We'll have more announcements later. You can find lots of kernels. And so I think we have the world's largest open source portable kernel library across NVIDIA, AMD, and now starting to turn on Apple, which is also really exciting and cool. We've got the serving components, which we don't have time to talk about today, but they're all public. You can go check it out. And so make it super easy to build and distribute servers. And so we're tackling this whole stack. And so one of the things we believe in is making this accessible. So yeah, you can hit install, you can use Combi, you can do all the favorite tools, and make it really easy to get up and running. And we want to make this super fast and easy. We'll show that later. And so as you dive into this, again, like your curiosity is the only limitation to what you can do. And you can dive into the Mojo Stamp library, or dive into kernels and modeling APIs. And we've also said, of course, we're open sourcing Mojo next year as well. And so this is all part of our big plan to like build into this and really push this entire ecosystem forward, because we know the stakes are high. We know this is really important. We want to do, and we want to feel a great responsibility to this way. So that's my part. I think this is a really exciting time. I think that AI is so critical and important to everything that we do. I want us to be pushing this forward. I want us to be relentless. I want us to be challenging the state of the art. I want us to be pulling in the best ideas from wherever they are. And so I think Ferris gets to kick things off. Actually, we'll do Q&A first, so you're safe. But to talk about the graph compiler and then dive in. So if anybody has any questions, I'm happy to take them. get to the people that actually have technical content to share. So,
Question.
Yeah.
I'm new to the entire system, so.
Thank you. I'm new to the entire Mojo ecosystem, and a burning question for me is, how's the support for the Windows environment?
Windows is one of the things I'm sad we don't have great support. We do support WSL, and so that exists. And so Mojo fully supports that, and you can fully use that. We haven't had time to invest as much as I'd like into it. If you'd like, please do bug us about that, and we can talk about it.
I would definitely bug you about it. I feel like that's a very important missing piece in the industry.
Yep, I agree.
So this is actually complete news to me. I actually thought Modular was just like building an acceleration layer, and just seeing that it's much bigger than that. This event is great to get the news out, but the news needs to be out a lot more.
Yeah. Also, so you're surprised we're building also an entirely new AI framework. There's a reason we haven't been talking too much about it. Right? So first of all, it's only now just becoming real. Right? We've been building components and we've been using it. We've been talking about performance and results and deliverables end to end with this, and it's been very important. But I think now, January, like we're coming together. It's like getting actually pretty good. Now we're not doing training. But people say, oh, okay, well, I'm not interested in that, and whatever. Right? Just an inference thing, fine. Someday we will. So we'll get there. And this is part of the philosophy that I bring at least, which is doing really hard things takes time. And so you have to be careful. I think we learned that with Mojo 0.1. You have to be careful when you kind of declare success, because if people come in and it's not actually good, that's the impression that we make. So we've been building the open and all this stuff has been out there. But even today, we're like, with y'all, we're sharing some of this stuff, but I think we'll make a lot more noise about this next year.
Nice.
May I? Thank you. Thank you. I lost track of the evolution of the license for Mojo and Max and the whole ecosystem. And I'm nearing to a point that I need to start having convincing answers about where the license is going to be in the future, right? I know it's a kind of an unfair question, but can you maybe share a little bit more how you would hope the license would unfold? Because I know it's free. We have to tell you that you're using it, but there's also the idea that if you're using it for inferences, there might be a charge later on or something like that. So something more about the license would be very helpful.
Yeah, so you're saying like basically how's Modular make money? Yeah. So we are building a managed cloud platform. If you have interest you want to manage, come let us know. But Mojo is roughly competing with Rust or CUDA or other free technologies. Max is competing with other free technologies. We want to do that. And so licenses, take it easy, to scale it arbitrarily on NVIDIA. We do ask you to tell us about it because we'd like to know about that and work with you, and maybe we join blog posts. If you would like to work with us, well, we have limited engineering, and so then we can talk about relationships and things like that. But no, you can take this and use it.
Okay, thank you.
Quite important. We do have other relationships and partnerships we'll be announcing next year, which are really cool too. And so there's more to come.
I have one question. My name is Dhruv. Great to connect again. And thank you for these meetups. It's such a great opportunity to again, be a part of this technology as you're building it. I'm coming from a physical AI context. I don't know if this question has already been asked. Would love to know if you're thinking about edge hardware or AIoT. Is the new word I'm hearing around this. I would love to hear your opinions on this. I'm Drew Beebe. I'm founder of Solo Tech. Just interested in this.
So we have not announced anything with edge hardware. I'm trying to keep the team focused. I would like to help the entire world, and so we'll have more to say about that next year. And it's very clear that Modular cannot do all of the hardware. So we'll get there.
I had a project where I needed training, and I really liked being able to use Mojo for the kernel and stuff. And I keep hearing this sentiment. There was some stable HLO MLR thing in Zig that says the same thing. Oh, we're just inference. And I'm at the point now where I have to make my own language because I don't understand why does no one want to support training. Like you say, it's hard, but I don't understand what you mean when you say that.
Okay, you're on to me. It turns out that training is also matless. Turns out that, again, we're arbitrarily general. Turns out that even though modular, again, is underselling what we're doing, other people are using Max to do training. So if you'd like to do training, go check out Napla. It's a community project, it's super awesome. It does both Jack style and PyTorch style training using Max today. So Napla, N-A-B-L-A. And so you can also ask us later. And so yeah, so turns out that again, what we're trying to do is we're trying to like set expectations. There's a lot of people that have been very excited about what we're doing, and then I make the mistake of saying, yeah, and we'll do training. And then people say, today? I'm like, no, I can't. We need to get some other things finished first. But this is the great thing about community, right? Is that modular people don't have to do all the work, right? You can go build that. You can go work with someone and say, hey, like, how about this? And what about second order derivatives or whatever your jam is, and go work on that. And it's just math, right? That's the beautiful thing. All right, how about I ask Ferris? And Ferris, would you like to dive quite a lot deeper into what is this thing and what's inside the nuclear reactor? All right, here we go.
All right, good evening everyone. Thank you for being here. My name is Ferris, and today I'll present to you this thing called the graph compiler. So, not working. Oops. Click twice. Okay, how do I go back? Red button. Yeah, okay. So, the agenda today, I'll present to you with the graph compilers at a very high level because I'm sure you're wondering, like, what's this graph compiler? Everything is graph in compiler, so why do we call it that way? And then I'll talk about extensibility, which was the cornerstone of what the graph compiler can do. Then the mod dialect, which is what we use to do fusion, all types of optimizations. And then I'll show you how every single thing the graph compiler culminates into anything Mojo. That's the Mojo codegen part. And then we'll end with a Q&A. And disclaimer, I'm sorry in advance, I'm about to effectively squeeze 3 or 4 years of work into what I effectively have like 15 minutes. And so that's almost impossible, so if you have questions, just talk to me. All right, so Modular is doing AI inference, and it's distributed, and at the sort of core of it, there's this framework called Max. And inside Max, there's our beloved programming language, Mojo. And the graph compiler is this concentric circle around Mojo. It's not Mojo. It uses Mojo, it ingests Mojo, and you'll see everything later, but it's not Mojo. And so in deep learning infra, when we say graph compiler, what we mean is this very high-level diagram. We mean that, at least for our graph compiler, we expect you to give it a deep learning graph. That's the model.mlir. It's based on MLIR. And as well as a bunch of, a package of kernels, essentially, written in Mojo. And the output of the graph compiler is this model.math. Math stands for model executable format. And it's the executable we run on various hardware, depending on what you were compiling for. And so that's the high-level overview of what a graph compiler is supposed to do. So if you're in PyTorch or you use the graph API and you build your operators, what you'll get is this DAG of operators that we call a graph, and that's why it's called a graph compiler. And if we go by dialects, there are roughly 3 phases in Modular's graph compiler. The first one is RMO and Mo. Mo stands for modular operators, and R is for relaxed. It's the same thing as Mo, it's just more relaxed around shapes, so you can do like implicit broadcasting when you add 2 answers, for instance. And this is your typical high-level deep learning operator set. So here I have an example, very simple model. It supports dynamic shapes. Those are the N, M, and K letters you're seeing on the screen. And you have your matmals, your adds, your activations, typical stuff. You're probably familiar with this. And the design is very risk-like. We have only 135 operators as of today. That's small, relatively speaking, if you compare to other graph compilers. Vertices are your operations, and the edges are your tensors. And we also support side effects, meaning like you can change like an input tensor. You don't have to like create a new one every time you run an op. And we do various optimizations of this level, like symbolic folding. We know what the ops are, so we can fold them. We do shape inference, constant folding, and many more. I'm just summarizing the important ones here. The second phase is MOG. I'll talk about it more later, but at a high level, MOG stands for Modular Graph Generators. And what you were seeing on the previous slide with the matmul, this is what it turns out to be in MOG when we lower it. It's a structured kernel representation. This is what we use to do lambda-based fusion. And it's destination class style in the sense that you've probably written kernels in Mojo, and what I mean by GPS style is that you'll get the output as an argument to your kernel, as opposed to like returning something new. And this does the conversion inside the MOG kernel. And the various optimizations we do are element-wise fusion, prologic cloud fusion, view fusion, small constant alignment, a few others, but those are the main ones. Last but not least, the last phase of the graph compiler is MGP. MGP stands for Modular Glue Primitives. These are the primitives that we use to interact with hardware, so allocating memory, executing stuff, working with shapes, and extracting information from different objects. And all of this culminates into MIDI Mojo and then JIT compilation. Little note on JIT compilation. It's like the head of time compilation in this graph compiler, but we call it JIT because the kernels that you wrote that I presented on the first simple diagram, they're not elaborated. It's Mojo like parameters. They don't yet have a value, and the graph compiler will take care of giving a value to all those parameters, and that's why we call it JIT. And the optimizations you find in this phase are sequence fusion, which is just inlining a bunch of kernels just to reduce interpreter overhead when you're going to finally run that graph of ops, memory planning, and thing I like to call runtime constant folding. So if you don't want to explode your compilation time, you're going to just move that bit of code into the init phase of the model. So you do it just once when you start up the model, and you don't have to do it later. And so what I described so far is a very simple graph compiler. There are some cool things, right? But I've omitted the most important part. I like to do on purpose because I want to ask a question: like, how do you design a graph compiler that's going to be resilient to this fast pace of change in this industry? Like every month, I think there's a new attention flavor. I can't keep track. I stop reading papers. I just have like 20 tabs of papers I never read. You probably experienced the same. Every year there's a new hardware generation, and then new instructions, and then you have to use those instructions because if you don't, you'll get peak performance. Peak performance is non-negotiable. So how do you design a graph compiler that's going to be able to give you performance, but also be resilient to change? Because if you commit to something and then things change, you're now back to square one. You have to redo things, and the more you build something, the harder it is to rebuild it, and so you get the point. So before I give you the answer, I'd like to model the deep learning optimization space here. It's a 1D spectrum. In reality, it should be like a hypercube of trade-offs, but I don't think we can visualize that as humans. So we'll stay with the 1D here. On the left or right-hand side, there's kernel-centric. If you're writing kernels, if you like CUDA, if you like module kernels, that's the side of the spectrum. What's really great about writing kernels is that you can get all the performance you want. It's fast to compile because generally it's very close to what the hardware is going to do, so there's not so much a compiler can do. You get predictable behavior, especially, again, because the programming model is close to the hardware. It's fully extensible because it's just code. You can do whatever you want with it. And fully debuggable depending on what the vendor provides, obviously. But the biggest problem with just writing kernels is that you get low coverage. Every time there's something new, you have to write something for it. And so it doesn't really scale. But on the other side of the spectrum, you notice like they're just reversed. You have what I would call more like compiler-centric systems for doing AI in general, with AI infra. They typically provide you like what I call productive abstractions, like a DSL, or that offset that I showed you in Mo. That's a high-level abstraction that you can use to program your hardware, technically speaking. And the cool thing with that is you get high coverage, but then you get all these bad things. You get a lot of the time subpar performance if you just use those. Compilation time can be slow if there's like a search space, so think TVM, think about that, and TVM can lead to like hours or days of compilation time because you have to search that search space. And unpredictable behavior, because again, the more your programming model is far away from what the hardware does, then you can't really predict what it's going to do. It's a compiler, it's a black box from your perspective. And extensibility is restricted by what the programming model provides you. If you try to do something that goes outside the box, that's not going to work. Or sometimes it does, but you get bad UX. And debugging is just not great because you're debugging like operators, but the hardware is running instructions, so how do you map the two? If we look at this, at that 1D spectrum, we can conclude that there is no finite operator set, DSL, or programming language, or model that can reliably cater to all the needs of deep learning. What that means is that whatever point you pick on that spectrum, you're probably wrong. And that's the conclusion we had at Modular. And if we go back to the question, so okay, I can't pick a point, so how do I design that graph compiler? How do I make it resilient to change it? No matter where I go, I'm going to be wrong. And it turns out the solution we found was we're going to hedge by investing in programmability and extensibility. What it means for Modular is 3 easy steps. The first one is our beloved Mojo programming language. We have a productive way of doing kernel writing. So what that means is Mojo, you've probably done C++ or other programming languages. You can compare them all you want with the language wars, but we think that we built the programming language for AI, and it shows. Like what I'm showing here on the screen, there's a blog post on this if you want to read it. We managed to get like in just 2 weeks state-of-the-art performance on MI355, which is incredible. Like I've never seen something so fast from developers. Yes, we have excellent engineers. Yes, we need those experts, but we also need the tools, and that's the first step. Second step is you design your graph compiler as mostly kernel infrastructure. What that means is you're going to be writing kernels, and when you find a pattern, something where a graph compiler can help you, you push that feature in there. The graph compiler is kernel infrastructure, first and foremost. And the last step is when it's time to get out of the way, you do just that. Meaning if the expert wants to do something, they want to enable some feature in their kernel or something that your programming model doesn't allow, it has to be easy and doable. And that's what the third point is. And the summary of all these steps is that write kernels, find a pattern, put it in the graph compiler. That's what has been mostly our recipe. It's very pragmatic in that sense. And so practically what it means is extensibility. I said that's the solution. I'm going to present to you the 2 building blocks of extensibility in our graph compiler. The first one is Mo custom. If you're familiar with TableGen, this is the definition of the op, this thing, this little weird language. And it's very high level. It's a knob that can take any operands, returns anything, can have arbitrary parameters. And this is how you do a custom op that's not in the OPI set, the Mo operator set. And it's very abstract, very opaque from the point of view of the graph compiler, at least initially. The second building block is Mo.opaque. So the same way Mo custom is like to kernels, Mo.opaque is to your arbitrary type. So your kernels don't have to just work on tensors. You can have your KB cache be tensor, but it could be anything else. You could have, I don't know, database handle in your kernel. You can do anything you want, and this is built into the graph compiler. And if we go back to the original diagram, because this is a first-class citizen sensibility, it means that you don't need to rebuild the graph compiler. You write your model, you put in custom ops and opaque, whatever you want in it, you just provide the kernel implementation. And then the JIT compilation that I talked about earlier is going to take care of specializing everything, actually compiling it to binary. But there's no like 30-page document that you have to follow to write custom kernels or anything like that. You just do it. These operations, from the point of view of the graph compiler, are just ops. right? They could have any name, any semantics, it doesn't matter. The graph compiler is not going to touch them. And so in a way, it's like a side channel for you to do anything you want in Max. So if you've been following, I said we write for kernels in Mojo. This is the signature of the MoMatMol kernel. It's open source, you can go look it up. And then I said that it's going to look like this in the graph compiler. How do you bridge the gap? Like this is Mojo, this is MLIR. You can find some things on both sides, but they're very different. How do I know that I can do fusion on MoMatMol and generate this structure here? And the cool thing about Max is that we have a vertical system. We can introspect Mojo. Mojo, like I show you example here, this is the implementation of MoApp actually. Again, I'm showing you real code, this is not pseudocode. And what you get at the bottom is the IR representing the code at the top. This is in the lit ballot. Mojo doesn't have an AST, parses directly into a ballot, and we can programmatically introspect this. And so I show you with the highlights here, you can know what it registers, what it is. In this case, it's an element flies up, and the fact that it's adding two things. And then you get all of this in the IR, and you can reuse it. And that's how we build these structured kernels. And this is the mod phase of the graph compiler that I promised I would talk about. The thing you're seeing here is the structured kernel of MoMatMol. And you can find in light blue, that's a lambda. That's what we use to do epilogue fusion. And so I'm not going to go back to slide because there's a delay, but you've seen the matmol, it has output fusion enabled, and that's how we know that we're going to be able to do epilogue fusion. And here I'll show you like an actual intuitive example. Remember the original graph I showed you? There's a matmol, broadcast, and add, and activation, which is Relu in this case. This is everything fused into one singular kernel. So I'll just give you some time to stare at this. Obviously, you can rewind this on YouTube at some point. But our fusion is effectively lambda-based, and that's how we do it. So if you've been paying attention to this, mod fuses operators not based on what they are, but how they're written, based on the signature of the Mojo kernel. So everything I just presented on mod, about fusing things and looking at structured kernels, all this works with custom ops as well. And this is thanks to having a vertical stack and having your own programming language, being able to introspect that and do whatever you want with it. And the last phase of the graph compiler is Mojo Core Gen. It's work in progress because we're hard work on finishing this. We're near the end. Can't give you a date yet, but we're very close to releasing this. And what you get on the left-hand side, that's the fully fused structured kernel I showed you like 2 slides ago. And this is the generated Mojo. The graph compiler generates Mojo. And you can see the relation like it's almost one-to-one. And this is something you can stare at, modify, debug, whatever you want. Even the MGP stuff I presented at the very beginning, remember, even that turns into Mojo. So you don't just stare at kernels, you can look at what the runtime is going to do and do whatever you want with that. And the cool thing with making Mojo, because recall, like you're writing your kernels in Mojo, you're giving that to the graph compiler, it's going to parse the Mojo, and then not the graph compiler itself, but it's going to get the parsed representation, it's going to introspect it, and it's going to emit it again. Everything is Mojo, and the great thing about this is Mojo is human friendly. You can read it, you can debug it, you can modify it, and if you can picture something, some optimization or anything done in the Mojo programming language, then it can be done, because we're not, like, the thing we emit is a general purpose programming language. Of course, we're constrained, like we're not getting literally anything in the graph compiler, but we're not stopping ourselves by using a restrictive representation. What you're going to get at the end is Mojo, and that's what you give as well. So that's your degrees of freedom, so to speak. So that's what we have today. We have relatively basic fusions. We have partial Mojo Core Gen, almost done. But thanks to this sort of architecture, we're going to be able to do more fusion, mega kernel being the ultimate fusion, you could say. We're going to improve our kernel registration, do vertical debugging, because remember, yes, you have a programming language, you can put breakpoints, you can do stuff at breaks if you want to, but you're sometimes building the graph with the graph API, and that also has to be part of the debugging experience, because it's not just the programming language, and we're going to do just that. Also going to improve the readability, like I'm actually going to go back to slides for free. To see like all the variables, it's obviously computer generated, but we're going to include that, don't worry. And that's it.
This is awesome stuff, but where the bits hit the wire, I mean, in terms of your support in Apple Silicon, which is why I'm here, I'm really interested in that. Your support in the NVIDIA, Blackwell, and AMD. So, how is it that is it the lowest common denominator to be able to have this, Mojo code that will run at the fastest on all of those different, GPUs? Like, you maybe talk a little bit about, that magic that happens to be able to write once, run fast everywhere.
If you're referring to kernels, can't hide it. Like, we have to be aware of the target. Like, if you're doing MacMols, you can't get like maybe 50% of peak performance by writing just one type of kernel. But the way we do it to get state of the art is sometimes even better than that. We have to be aware of the target. But the graph compiler, for the most part, what I presented, is hardware agnostic. GPUs and CPUs have similarities, and that's how we do fusion. Other more exotic hardware may not fit this model well, but of course, as I showed you, you can bypass that. But Mojo as a programming language makes it so easy to not just have a bunch of if statements, like, okay, if this hardware do this. We have some, not saying we don't, but a lot of code is shared, and the recipes for writing something like MapMol are so similar, and Mojo is so easy to use that we're able to support them so quickly with very good performance.
Okay, so have I read right that you're actually beating CUDA on certain types of MapMol operations? And that's kind of I'm really impressed that that is actually true, and actually I can know how they're able to be.
I'm the wrong person to ask this. I'm the graph compiler engineer. We probably have kernel folks here, I'm not sure. Seems like Chris wants to say something.
Yeah, I mean, I'm also the wrong person. I'm not a kernel expert, but first of all, you have to understand that all of these systems are very complicated. So if you take something like the CUDA, DNN, or CUDA-BLAST, MapMols, they have a mini compiler with them. Because you have to get, as Ferris is correctly saying, to get the peak performance, you not only have to know all the tricks, but you have to assemble them in the right way, you have to do specialization, you have to do enrolling, you have to do all this stuff. And so you can't just have like every shape permutation, every tall skinny, all the things in a stack of compile thing. And so we have smart people, but what we're doing is we're assembling the tricks in a way that we're getting better performance. Now, when we say we're beating CUDA-BLAST on that one, it's not by 10x. 6 to 10% maybe, but that's still material. The most important thing is that we're not worse. And so I think Ferris did a great job of explaining TVM and XLA and one of the AI compilers. The key thing to know about what we built is we're not an AI compiler. We're throwing that concept away. We want peak performance. We want the best. We want to assemble and integrate all this crazy ass technology these fine folks are building into a novel system that allows you to get the best performance without having the lowest common denominator system that we've all seen. And that's the only way we can push hardware forward. That's the only way we can get everything out of that next ASIC that is not actually an NVIDIA GPU or something. And that's the only way we can make progress in this industry.
May I? Sorry for the double questions, just nice. This is a very rookie but yet nerdy question. I think I understood only 40 or 50% of your presentation, but when you generate Mojo code, Mojo is very powerful and amazingly not complex of a language. But it does have one particularity because it lacks garbage collector, etc., which is the control of the lifetime of the variables, like copy semantics, like very well thought out. But when you're generating code, the concern is still there. So maybe you could speak about the techniques or whatever you use to ensure that the generated code is also generating the best lifetime for the variables, maybe extending them to reduce the opportunities to the allocation, or just banking on the eagerness of the allocate. I'm very curious how you control the generation time, the duration of the lifetime of the variables.
Okay, so the code that's emitted from the graph compiler, the Mojo code, it's not operating on very complex things. It doesn't use all of the Mojo language features. The reason we're emitting it is not because we need traits or anything like that. It's because something that's readable, it's better than giving like a binary or words like assembly, PTX or something like that, CD6. It's readable. And for the most part, what the graph compiler is generating is like pointers, small static arrays. And so we're not exercising the lifetime feature of the Mojo programming language so much that it matters, especially in large models. Those things, like even if you deallocate something a little too late, that's not a problem. But the graph compiler is mostly manipulating like pointers or really register-based things like, I don't know, integers and basic structures that are register passable, if you're familiar with register passable. And so, boring answer, we're not doing very complex things. It's mostly to give something back to the user that they can understand and modify and play with.
Thank you.
I'm kind of curious where the graph compiler starts and ends. So like, how does it integrate into Mojo or Python? I'm kind of trying to place, because one of the big questions is like control flow through a graph. That's kind of the limitation of a lot of the modern like Python DSLs. So you have to use a while like in a weird way. So like, where does graph compiler start versus just other Mojo code?
Right, good question. We support control flow, meaning our mo API set has mo.if and mo.while. We're not doing the sort of interpreter magic that PyTorch may be doing when it tries to find graph breaks and stuff like that. We have a way of building the graph you want to give the graph compiler, something we call the Python API or graph API. That's going to change. I think we have maybe something to say about this. So I'll defer probably to my colleague's presentation, but it starts out in Python. You build your graph. It's very straightforward, and no magic there, because we're here for performance, pragmatism. We don't want to have to play in an interpreter's bytecode to find where the graph starts and ends. So you will be explicitly building graphs.
Hi. So, part of my ignorance, I'm not sure I fully understood the presentation, but you did mention databases in there, and kind of wondering, like, I'm getting the idea that this compiler is what it says it is. It's a graph compiler. Is it meant? Is one use case maybe you want to compile like something like differential data flow over like a distributed system, something along those lines? And then following from that, I'm kind of wondering, like, if you were to summarize in one sentence what the essence of the graph compiler is, like what would you summarize that?
Right, so for now, the graph compiler is your typical deep learning graph compiler. It's gonna ingest bunch of custom ops, doesn't know what it is, not going to act on them except for fusion. But for the most part, it's interested in deep learning operator sets. So matmals, value, add, and everything. The reason I mentioned databases is because right now, today, if you try to build a graph with like a database handle or something, you want to do something in custom op, you can do that. The graph compiler is not going to get in your way. But of course, as things will evolve, I can't promise or say anything really, but if we find a gap somewhere and we deem it valuable to have something dedicated for it, the same way we're doing it right now for deep learning, we could do that. But for the time being, you have your side channel, you can do whatever you want with custom ops.
So again, this is, so by the way, like the internals of graph compiler is not something a normal programmer is going to have to know. We just thought that talking about this would be interesting. But a lot of what we're doing with the graph compilers, we're really flipping traditional graph compilers on the head. And so if you ask, I mean, there's a whole category of graph compiler people that are compiler engineers that work on these things. Most graph compilers were designed to integrate TensorFlow or PyTorch or Onyx or things like this, try to lower them, try to get good performance. And so most people think about graph compilers as a way to get performance. That's typically what people are. So Fusion is a way to get performance from operators. I think that's nonsense. So that's not what our graph compiler is about. Sorry, Ferris, I know you love performance. In today's world, if you want performance, you could just write CUDA kernels. Right? Right? A massively hand-fused CUDA kernel and you get performance. And so there's no way that a graph compiler is going to give you better performance than writing all of the ideal custom CUDA kernels by hand. And so no, the graph compiler is not about performance. What the graph compiler is about productivity, it's about scalability, it's about extensibility, it's about new hardware. And so what the graph compiler does, the short version, is it's a total productivity, scalability, portability hack. Because as Ferris is saying, what we're doing is we're saying like, look, no, we don't care about Onyx anymore. Like, Onyx is a good thing, and I mean, many people do care about Onyx. We're coming in from like speed of light of the hardware. And so if your output is highest performance, sure, you could write CUDA kernels, but nobody can afford to do that. Nobody can afford to rewrite them when your chip comes out. And so instead, what you want is you want to get, for example, Fusion, because now you don't have to rewrite all the permutations of all the different operators. Like, this is huge. This is what allows Mojo to move so fast. Like what Hassan and others are going to be talking about is like, again, you don't have to write MLR, obviously use our stuff, right? You're just programming Python. You have no idea there's a graph compiler underneath there. But it just means you get good performance and portability and all these other things that we want. And so, again, this is like compilers at their best. Compilers at their best are things that you can ignore. You don't know that you have. The compilers that people notice are the compilers that are misbehaving and crashing and forcing you to read MLR, or like looking at compiler internal thumbs. Those are bad compilers. The good compilers are the ones that are making you happier, more productive, and that generally you don't have to know that it exists. Now, this approach is like so fundamentally different than what anybody else has, in my experience, has ever done before, that it's like really crazy. And so the features, so full support for dynamic shapes, not just unknown dimensions, but fully parametric dimensions, where we track symbolically the shapes. Like that's actually really fundamental. That's what enables next generation even, right? These things are very nerdy. That's my cup of tea. But they're not things that people are forced to learn and use. It's the implementation details that come in the benefit of building this next generation stack. And so, you know, your question, I think the great question is like, how do you explain what the graph compiler is? It's about productivity. It's about scalability. That's what the graph compiler does. And you know, ideally, unless you want to look at generating Mojo code or something like this, ideally, you don't have to know it exists, which is also cool.
Any more questions? All right, I think that's the end for me. So now I'll leave it to my colleague that is going to present to you that Python thing that I got questions about and how we're going to improve how you can build graphs and different decisions behind this and how great it's going to be built.
Can you hear me well? It is my switch. Okay, great. If I can manage to slide. Okay, there we go. Thanks so much for coming. My name is Ehsan. I'm a product manager here at Modular. I work on Max. Today, I would like to share more about the new API that we published. And I also have a notebook that I'm going to show you. But for a bit of context, so before 25.7, which was our previous release, our modeling API, Max API, would look something like that. You can see some resemblance to PyTorch if you're familiar with like NN module, the way that you declare your model. But also you would have to write more, you would have to scaffold an extra graph and be more explicit about tensor inputs, type, and things like that. And finally, you will be able to compile and execute your graph. So what we have done for 25.7 release, we've introduced a new set of API. I'm going to also talk more about the API philosophy, but the core philosophy that we're after is we want to be more PyTorch-like. We want to have PyTorch-like abstractions, get good ideas, adopt good ideas, but also adopt them in a way that makes sense for us. So if I would just cover perhaps the input layer, you would guess this is very similar to PyTorch or actually the PyTorch code. And that's the intent. You would exactly write the NN module, and then the only difference is there's the call function, and then normally you will be able to create an input, call your model, and also compile your model. I'm going to talk more about this thing. We have an eager mode, and technically it's a lazy evaluation with eager semantics because everything is graph-based. And finally, you can also have your model compiled. This is very similar to Torch.com concept, but completely different methodology, and it uses our graph compiler and things like that. Now I need to switch my screen. Okay, there we go. Is this big enough for everybody? Okay, good. All right. So I've prepared an introductory tutorial, particularly for PyTorch users. And we're going to see side-by-side examples of PyTorch code versus Max. This is going to be mainly basic. And the code is also available in our Modular. If you go to Modular workshops, the code and the material should be on the Modular Mac December 2025. So the very first, sorry, yes.
You need to adjust it for the slide screen, the share screen. Yeah, we're not getting that.
Sorry, oh, sorry.
Yes.
Alright, so starting basics, how PyTorch does tensor creation. It has torch.tensor. You can pass it a linked list or an iterable. Torch.zeros, things like that. Very familiar API. In Max, we also have a tensor. The only difference is we have a notion of constant tensor, and we also have zeros, ones, things like that. You can compare the outputs, but one thing you might notice is the default, which I'm going to talk later, is basically Torch assumes the default is float 32, CPU, even if you have GPU, you have to be very explicit, but in Max, if you have GPU, it automatically is GPU, and even the default is bfloat 16. So quickly, the key difference, generally what I would like by the end of this talk for you to remember this kind of mental model and dictionary to be able to translate your PyTorch code into Max. Next, yes, I talked about the defaults. You can see, you can print them. You can print the default D type and device. Next is about device management. So here is this familiar PyTorch code, checking if CUDA is available. If available, you do .CUDA. Here, we have the driver API. You can import CPU and accelerator, right? And you can also, let me show you the output. GPU is available. And as I said, by default, when you create your tensor, it automatically uses the GPU. Here, you can transfer it to CPU. Looks very familiar. And you can also get it back by being explicit. Data types. Let's compare data types. So PyTorch has default tensor is float 32, or is float 16. You can also set the default for the data type for your tensor, be explicit like this. We also have the context manager that you can include that will basically dictate the default data type for all the tensors that are created inside. You can also cast a tensor type to a different tensor type. And yeah, very, very simple, familiar stuff. Next is NumPy or PyTorch tensor interoperability. PyTorch and NumPy, well, you can translate between PyTorch and NumPy with the familiar from Python or, from NumPy or NumPy.NumPy syntax. PyTorch relies on DLPack. We also use a DLPack, which is a data exchange format or protocol. So if you have a NumPy array, you can use tensor from DLPack. You'll get a max tensor. And also, if you have a max tensor, you can do NumPy from DLPack with a tensor in NumPy, back in NumPy. Also, we can do the similar thing with PyTorch tensor. Here, for example, I have a tensor on my device, and I can simply call tensor from DLPack. I don't need to move it to CPU or anything. That's the beauty of this data exchange format. And you will automatically get the correct data back or tensor back in max. Next, we have the functional API. So we're going to compare PyTorch versus Max. PyTorch has this torch.nm.functional that you can call. It's a beautiful API. For example, you can calculate value, GLU, all these things on a tensor. We also have exactly the same kind of API. You can see it matches. Similar thing with softmax, log softmax, things like that. Very similar. Matrix operations, mathmos, can create random tensors with torch.random. We have a dedicated random module, which in my opinion would make better sense. And the similar, or basically the same syntax as mathmos. And one thing we need to work on is basically when you're printing or representing multi-dimensional tensor in a notebook or things like that, you want better shapes. Here, unfortunately, we are flat. We need to fix this. Reduction, so you can do some mean, max, all the odd max, similar thing with max as well. We have for most of the, the well-known reduction operations, we have the functional format, like f.max.sum, mean, things like that. For some of them, we also have the tensor format, similar to PyTorch. Here, for example, mean, max. So this is in dictionary or comparison between API. Well, should be very similar. Perhaps the only difference here is with the reshape. PyTorch has a reshape, but also has the U. You only have the reshape. And also cast. So I briefly talked about random module. You can create random matrices. Same here. And now we're starting to get into more exciting stuff. Module system. So PyTorch and then linear in Max. You can also import Max, or here we call it module v3, but we're going to, in the next release, we're going to actually drop it, and then everything will be Max. And then the linear, you can also call it exactly the same as you would call a PyTorch linear model or any model. Embeddings, torch.npnn, embeddings, same argument. Here we have exactly the same type of argument. And now custom modules. So very basic MLP should look familiar. This is how PyTorch represents it. If you want to see the name and the parameters. Max.nn is also very similar as I showed you previously. So the only difference here that you need to remember is we do not have a forward method. It's just a call that you need to implement. One thing we have that is a nice utility in definition is we have the module data class, and actually NN module is a data class that you can also wrap it like this, and it will turn your module you don't need in it or something like that. Sequential, very similar. And here I made a custom, let's say, Lambda module that I can use it inside my sequential, and then in my Lambda, I'm using f.a as an example. Now, here I've taken a simplified version of GPT-2, GPT attention layer for hiding face. And I'm going to do some live coding. Okay. So what I'm going to do is I'm going to turn this live into a max code. So, and I'm going to do some mistakes. We'll see some errors, and then we'll be able to catch them and quickly be successful. So I'm going to, yeah, this is it, and let me also do this. Okay. So the first thing is, first of all, as I told you, all of our NN modules is based on data class. We don't need to do inheritance. Here we have the same concept, linear and then linear. We do not have forward method. We have call. One thing we do not have, or well, it's good to have, is a split method on a tensor. So we have it as f.split. You can, let me also quickly show you everything that if you go to our docs, for example, functional API, you can see all the API listed here. And also same thing for tensor and RAM. Okay, that's a very quick reference check. I told you that we do not have view, we have reshape. So reshape, we have the same transpose. This should be easy. There's a mistake here. We're going to see the error and we're going to fix it together. Let's do this. And there's also a mistake here. We're going to see the error. And I think that should be it. Okay, let's run it. Okay. The first thing is you see we do not have any dim. PyTorch uses dim. NumPy uses axis. We like NumPy in a tensor manipulation format. We are leaning more towards NumPy. So the only thing I need to change is change this into axis. Same thing here. Okay. And the second error is going to be about, split sizes. Yes, so I actually didn't include the tensor here. Collecting the split. Another thing, as I told you, is reshape is an error here. I need to just pass them all as, let's say, a list. And then we have, the same reshape. These are small fixes. Okay, there we go. We have turned the PyTorch code into Max. And it took us small time. And now we can continue with the full GPT-2 block. Let's go and uncomment the whole thing. Okay, you can see the parameters. I'm not going to run the model. I'm not going to pass this thing. We have more content about tutorials, things like that, which my colleague Michael is going to show you. The next thing is about model compilation and optimization. So what we have here, I had a model that I built. We can pass it some random input. So this is an eager output. And later I can, I'm going to compile my model. And then we're going to also see the compiled results. So as you can see, they match. One thing that I should highlight is the model type itself is a class that we define. And when we compile it, it becomes a function. Here is a very quick and dirty benchmarking for eager mode versus compile mode. Eager mode is very useful for debugging and development, and for production, you will get the benefit, you will get all the benefits of a graph compiler when you do model.compile. So very quickly, sorry for the color mismatch. So the numbers do not really matter that much. The order matters here. You can see, for example, when you compile your model, it's about 1,000 times faster. So as a quick cheat sheet, torch.nn, max.nn, torch functional, max functional, the way that we define tensors, modules, the only thing that is different is call versus forward. Operations are the same. You also have the equivalent of functional versus tensor-like. And for inference, PyTorch requires what we call val. Evaluation, note that now compute the gradient and also compile your model later, for us, we only need to call a compile. And as the last series of examples, I'm going to also show you some Mojo code, because to be complete, I'm going to show you how to write a custom ops and how to integrate it in this new API. So if you've never seen a Mojo code before, I mean, first of all, we have this fantastic Mojo Jupyter Magic. So you can import Mojo.notebook. It activates the Mojo Magic for you. And I mean, here is basically a hello world. In Mojo. Next, this is a simple vector sum in Mojo. I am going to use all the libraries that are available when you install Modular. So we have the concept of layout and layout tensor in Mojo. So this is a very simple vector sum of two layout tensors, x and y, and the output. So the way, at one time, I was specifying, we have the keyword compile time, which basically does the computation at compile time, obviously. Defining entity 5 as an example, layout, and I'm allocating, let's say, five float 32, and I'm passing the pointer and I'm initializing my layout tensor. Same thing for x and y as an example, and I pass them into vector sum, and we can see it. Next is a similar GPU kernel. If you haven't coded any GPU, the only thing for now that's important is you can take the whole thing, you can copy paste it, and the fundamental idea behind GPU is replacing for loops with threads. So have a concept of global ID, that's the location where the thread is, and you're doing bounds checking and then doing the sock. For runtime on GPU, we need to do a little bit more. We have a concept of device context. So we're creating a buffer on host. You're filling them with, and also I need to mention that when we see enqueue star, these are async functions. And then we create the layout tensor from the buffer. Same thing for x and y, initialize them. We're compiling our kernel. And one thing that we have recently, actually we have added, is the ability to do type checking for the compiled modules, for the compiled kernels. So here, enqueue function check is doing the type checking, and we let the computation to happen, and finally get the output. So being able to print the output, we need to move the buffer into host and being able to access it. So in this example, as a continuation, I've taken my CPU kernel and my GPU kernel, and what I'm going to do is we have a concept of custom ops, which we're going to see. That means that it's going to, there's a struct in Mojo. You need to have a decorator called compiler register. And it's a struct that is going to encapsulate all of your kernels depending on the target. And you're going to see the examples for how to use it in Python. So Here, if the target is CPU, I'm using my CPU kernel. If the target is GPU, same code that we saw before. And now I also should need to mention that for custom ops, we need to package. Mojo.package outputs upstart. I can show you here, upstart Mojo package that we are going to include in our custom op or custom function. So if you remember, I talked about functional API. We have also the notion of f.custom that is going to use the same name as I register for my custom op. And here we have, let's say, two inputs, x and y. X is 10 tens, and y is 10 ones. So adding them all up. So x and y initially, they exist in CPU. So if I call my custom vector sum on x and y, I'll get the CPU kernel fault. And if I move them into accelerator GPU here, you will see that it automatically uses the GPU kernel. And here we have a unified way of using our custom ops on Mojo in Python. There's no build system involved. Imagine if you want to do the same thing in PyTorch or other frameworks, you would need to write C++ code, have your own build system, build this, maybe shared object, and have a particular setup in Python, being able to load it, and then we'll be able. Here we have a very seamless setup. That's it. That's the end of the notebook. There's a lot that I haven't covered. How do you load a model into how do you load the weights of a model, things like that. That all of them are covered in our documentation. Please do check them out. We have a reference of GPT OSS implementation. If you go to Modular code base or GitHub repository, under Max Pipelines architecture, you will be able to see the GPT OSS module v3. You will be able to see the GPT OSS, how we implemented it using this API. And all the details should be there. And my colleague is going to also talk about more educational content. So I'm done. I think we can do some Q&A. Good? Okay.
So I saw, a lot of it was FP32 and BF16. In a very specific case, like, the latest Blackwell, they have FP4. So that just got me thinking, could you have just done FP4, or is there support for that?
Yes, so what we are working on is FP8 and also some FP4 kernels. Unfortunately, I do not have examples here, but we do support FP8 and FP4. Yes, so I should be careful. I don't think we have full support for FP4, but yes, we have some support.
Hey, Hassan, when are you going to rip the experimental off?
Yes, okay, so in the next release, end of January, we are going to move all these API out of experimental. We want it to be deliberate, we want it to catch all the bugs, we want feedbacks from you, let us know if there's any sharp edges, and we can fix them quickly.
quick question about the API and like the small syntactic differences from PyTorch. So it's not uncommon, for example, for data frame libraries like pandas to polars, people will try to preserve, the exact API to the greatest degree possible, just because, it's just quicker to transition. Why make any differences? I was curious.
So your question is why?
Yeah. Why
the
keep the API like as close as possible?
Right. So, for example, one major difference is between forward and call. I mean, Max is for now is all about inference. We can call it forward. Give us feedback if you'd like to see a different type of data.
We should call it forward.
We should call it forward. Okay, that's a good. If you see the PyTorch implementation, basically forward calls the call. So PyTorch also has call, but it's not used for the programming. Small differences like you saw maybe some APIs you do not have the tensor method, maybe the existing functional format yet. Let us know if you would like to be fixed. We would like to be as close to PyTorch as possible. But also, we have our own philosophy, for example, dim versus access, things like that. These are small things. Let us know if you hate them. We can definitely do something about it.
Sorry, so you're totally right. Right, so you're both totally right. So where there's no good reason to deviate, we should be the same. So let's use forward. Seems fine. It's also why it's experimental still. We want more feedback and more things to be pulled together. But also there are intentional changes. So we call them default 16, for example.
Exactly.
So there,
Defaults. Yes.
There are certain changes that are intentional because we're learning. We want to actually be forward-looking and just get off and do that. But it's just like Mojo's relationship with Python.
Yes.
There are many things that we could have, quote, fixed that are superficial with Python, but instead we should just embrace the standard and therefore make adoption easier. So plus one, if you have suggestions, please let us know. We'd love to pull those improvements.
Earlier I was asking about like the control flow of the graph. I'm also curious about, it looked like there was some MLIR lowering. So I'm curious, in compiler mode, it kind of makes sense, how you would trace that, but I'm curious how that works with the eager mode. And when it comes to like off registration, like what the relationship is between the graph compiler and what you just showed with eager.
So if I understand your question correctly, you are asking about the relationship between eager mode and compile mode from the graph compiler point of view?
Yeah, so is that, like, for instance, it's unclear to me right now whether, like, what relation eager has with the graph compiler, but Modular compiler, whatever the compile function was there was a clear, like, okay, obviously this is going to like map to some MLIR PSL and then lower it from there, but eager is not as clear to me.
I think this is something that I'm not an expert. Perhaps Chris or Chris can help answer the question about the differences between eager and compiled mode from graph compiler and MLIR.
So so we're intentionally making this similar to PyTorch. That's a strong goal. But we're coming at things from a different place. Right? PyTorch started with training, started with eager mode, started playing through the frontier of PyTorch 1 of deciding eager mode is a good thing, and dynamism is all very important, and then discovered that accelerators keep getting faster and faster and faster, and they evolve on eager, right? And so then they've done a lot of things with that are really innovative and really cool, like tracing Python bytecodes and Torch Dynamo and all kinds of wacky craziness, which is very impressive, but it also kind of makes PyTorch 2 unpredictable, and we start tracing Python code and trying to make dynamic Python code static. Some demos can work really well, but like it just becomes very frustrating. So what we've done is we said, let's flip the narrative. Let's build in performance first framework. That's why Zasan kind of made fun of us at the beginning. He's like, yeah, well, if you look at the graph API, it was very low level, it was very painful to use, but it was never the intent that that would be the actual programming model for Max. This also goes back to the question of why not talk about this earlier. Like we're just building into the point where we're starting, and we're not quite there, but we're getting proud of what we're doing. And so you need graphs for performance, you need fancy graph compilers like Chris is talking about, but then you start to say, okay, well, I don't want to be tracing Python and trying to extract things. Instead, what you do is you start from, cool, I can bring eager mode into the system. And so the short answer to your question is, like, if you have an if statement, like one side will execute, and we're not going to try to do heroes to parse it. We'll make it explicit, and so you do actually stage the if into the graph, and you can do that in these operators. But what we've seen with a lot of models is that a lot of models are compositions of other people's work. And just like Hassan is showing, you can compile the entire model, you can compile subgraphs. And so if you're moving into other people's layers, like you can fuse it just a layer example, and you can have hybrid, eager, and compiled models. And this interplay is actually really nice. And so the one major thing aside from the get polish, which we do, is compile time. And the eager mode compile time in the December release, November release, was really slow, so I can fix in January. And so we're really excited about that because then it's really interactive and it feels good like an eager mode is supposed to. But now, again, you get full performance graphs, and they actually work well together. These all the same operators, all the same custom ops, all the same thing. Like it's like the same thing designed together instead of being like compile mode is kind of a different, ugly stepchild of the eager mode. So that's what we're doing.
So to directly answer your question, eager mode is eager mode in quotes. So we've done a clever thing. So all of our stuff is built on the same stack. So you see, you saw Paris talking about the graph compiler. The graph compiler is built on Mojo because it generates Mojo kernels you're specifying, fusing, and so forth. This new API that you see here is built on the API for the graph compiler. And what's going on behind the scenes for the eager mode is that it's materializing a graph at the point when you request a result. So it's eager in that you get the semantics of eager functionality, but you get all of the capabilities of our graph compiler, and it's building all the same infrastructure that you see for everything else. It's just a different mode of interacting with it. It's like the semantics that you get versus like defining everything in advance. So
yeah. Technically, it's lazy eval with eager semantic, and then when you print or when you dot item, it materializes.
Is it also compiling then?
I'm not sure if we have differences. There might be some differences, or there might be some optimizations that are turned off for the performance because we want eager compilation to be as fast as possible. There might be, so we're working on it, but eventually I think we will figure this out. Yeah.
So it kind of sounds like a bit like Jack's eager mode, where it's like it's actually just on the fly trying to compile. So it sounds like you're sort of building an eager semantic over the compiler. It's still
Yeah, so definitely related to Jax. Jax has a problem, which is it's built on top of XLA. XLA is fully static shaped. And so every time you do something, it has to go recompile things and specialize and change dimensions and then recompile it. And that's literally what this year release is doing, which is why it's slow. So one of the cool things about y'all's smart people's work is that our graph compiler and our entire stack fully supports dynamic shapes. And so the January release, one of the cool things it does, it says, okay, well, fusion is really important. Turns out, like, you don't want to do a mammal and then relative, right, for example. The shape specialization is actually optional. Shape specialization doesn't affect your memory code. Shape specialization removes some, constants, and like it's actually not that big of an optimization. It's important for inference, but for eager mode, you don't need it. And so what we're doing in the January release, we're saying, cool, don't specialize on shapes. Just actually use the fully dynamic shape version, which is something that Jax can't do. And what that does is it gives you a fully predictable, fully in control system. And yeah, you can specialize if you'd like to, like you can have power user features, but your eager mode doesn't recompile everything because you're not specializing on stuff that you don't actually need for performance. So this is why it's like this very unique blend. Because again, like we're finally building high enough that we can actually surface the power and the benefits is just easy. So that's really good.
That answers the question. That's the reason why I had to stop.
Yeah, the shape specialization stuff is why I had to move my project off of JAX. But I still needed the compiler for performance because running a for loop in Python is, I can't think of a slower output. Yeah, it makes a lot of sense.
All right, yeah, thanks so much.
Hello again all. I'm going to be brief because I don't really have another presentation. This is more of an invitation. You heard a lot from Chris about how we're developing a unified framework to build, optimize, and deploy AI workflows. You heard from San. The new API that we have, the Eager Model API, allows for a really intuitive way to build models that's easy to debug. And what we want to do is we also want to make that simple platform really simple to learn. And so we're aiming to make the single best way to learn transformer architecture that you can find. And that's this book, Build an LLM from Scratch from Max. I developed this with a technical writer here at Modular, Patrick Ratchford. And this is live now. You can go to llm.modular.com and see this tutorial. It will walk you through every step of developing the architecture of GPT-2 using the Max Eager Model API. And let me start with why we did this. We were really inspired by tutorials from Andrei Karpathy and by Sebastian Raschke on building GPT-2, on building an LLM from scratch. These are very popular, successful tutorials that help you learn the architecture of the now ubiquitous transformer architecture. However, we really wanted a tutorial that would walk people through how to build that architecture using the Max framework. And so the result is this tutorial you see here. There's 12 steps, you can see the chapters on the left-hand sidebar there, that walk you through causal masking, model configuration, layer normalization. I'll even show you one of the steps here, specifically how do you do multi-head attention. If you're familiar with the attention is all you need paper, then we need to implement multi-head attention in order to complete the GPT-2 architecture. And this book allows you to clone it down. You can see steps in the text, you can see steps and comments, and you basically fill out these to-dos. And through these steps, you both learn how does this API work, what's the syntax, and how can I access the documentation and build something with this, but also how does a transformer model work, and what were the architectural decisions that impact its performance. Additionally, all these steps are interactive. If you complete a few steps, then you can run the tests and get feedback on what you did correctly or what you're missing. The idea is that you're not in the dark as you work through the various steps of this architecture. We really wanted to build on a popular series we have. If you're familiar with Modular's journey, you might know our GPU programming puzzles. I've heard from developers that they found it the best way to really understand GPU programming because it's hands-on, interactive, and really high feedback. And so we wanted to do the same thing for transformers. This is all live and open source now. The things that you'll learn transformer architecture, you'll learn why these architectural decisions matter, and you'll learn Max framework. What's next for our tutorial? We are actively accepting community contributions. You can go flag an issue if something doesn't work as you expected. You can submit a pull request. We actually just merged our first community pull request this week. Someone saw an area of improvement, made a suggestion, and we implemented it. Things that are coming ahead, we will continue to improve pile times in the API as new API features. This is a rapidly changing API. As new features are developed, we will reflect that in the tutorial itself. You can also expect us to expand to additional model architectures. There's kind of a landmark architecture in GPT-2. You can learn a lot about transformers in a fairly accessible format by working through GPT-2. But there are other things, maybe cache, that you're going to want to learn at some point if you're doing model development. And so we're planning to continue to expand this book, and then at some point allowing you to serve custom models and go through that whole process yourself. I encourage you, if you're interested in learning more about transformers, please check out llm.modular.com. Come find me after this if you have questions about the tutorial. We really want this to be the best learning opportunity for you. With that, I will turn it to my colleague Connor to close this out.
All right, a big thank you, first of all, to all our speakers, to Michael, to John, to Claire, to Chris. Thank you all for walking us through the Max framework tonight. You guys absolutely crushed it. Huge shout out to everyone who's asking questions too. It's just really fantastic to see the energy tonight. I'm Connor. I recently joined Modular to lead technical ecosystem, so I am literally week 2. So that's why they gave me the closing notes and not a full tech talk here. So I promise to keep this very brief. First off, we are still here for another hour, so feel free to hang out. We have dessert in the back now. There's still food, there's still drinks. We'd love to chat with you. If you have more questions, we would love for you to come talk with us about them. If you have ideas for what we should be building, not only should you come talk to us about them, but you have the opportunity to build them with us. Because if you're interested in getting more involved, whether that's contributing to Mojo, whether that's helping us build Max, or just staying in the loop, we would love to work with you. We have people who are already building off of Max. This is very real. There is much more coming on soon in the new releases, but PRs are already being merged. We're adding to the language. Mojo 1.0 is coming even. Some of you may have heard of that. I know Chris is delighted to talk about that even more very soon, and we just published a great blog post that is a fantastic companion to everything we're talking about here at the Max Framework. But we would just absolutely love for you to come build with us, and you can obviously join us in Discord, our forum, and everywhere else. Those links are all over our website and at our /community page. And as I mentioned, we've got a lot coming in 2026. We're going to do a Max hackathon even. We don't have an exact date for that yet, so stay tuned. You're all going to get an invite, don't worry. We'll make sure of it. Probably February or March though. And we want to give you the opportunity to get your hands on with this, but if you are ready to do it today, great. We have much of this on GitHub. We would love to work with you on it right now. And finally, I would love for you to help me with one more thing. So obviously the speakers here, huge shout out to y'all, but really this event would not be happening without both you and the community, but a lot of folks behind the scenes. We have Anara, we have Mike, we have Paige, we have Roxy, Courtney, Daniel, Jason, and too many more that I didn't name, and I apologize for that. So if you join me in one more round of applause, everyone help me. Thank you all so much for joining us, for the excellent questions. We are so excited to build with you the rest of the year and in 2026. And please stick around for some more food, and we'll answer your questions. Thanks so much.